Electromagnetism. You might have heard of electromagnetism before in your daily life. In the Marvel universe, which is where these characters come from, some people have the power to manipulate their surroundings using electromagnetism. In real life, electromagnetism is sometimes used in roller coasters, trains, and lifts. In this presentation, we will learn more about what electromagnetism actually is. Electromagnetism. A permanent magnet, for example a fridge magnet, has a permanent magnetic field around it. Magnetic fields are invisible, but it is possible to see the effect they have on other objects. Iron-based objects are always attracted to permanent magnets. We can see a permanent magnet here and some paper clips being attracted to it. Iron filings and compasses are very useful for showing the effects of magnetic fields. In the picture on the left, you can see a magnet in the middle, and the iron filings around the magnet are showing the magnetic field. And on the right is a diagram of a compass and the magnetic field next to that. All permanent magnets have a fixed north pole and a fixed south pole. Magnetic fields can be drawn using magnetic field lines. Field lines always point to the south pole and are closer together where the magnetic field is stronger. Magnetic fields also exist between magnetic poles. You can see that in the top diagram we've got a north pole and a south pole, and the magnetic field lines are travelling from north to south. In B, you can see that there are unlike pole attractions, so between the two poles we can see there is an attraction, again pointing from north to south, and then when we put the two same poles together, north and north, they do not attract, so there's a repulsion there. A magnetic field can also be created by passing a current through a wire. This will be a weak magnetic field. To make the magnetic field stronger, the wire can be made into a coil. This is called a solenoid. This is a diagram of a solenoid coil. The electromagnetic field due to the flow of current is shown in purple, and we see the current going in on the bottom left and the current coming out on the bottom right, and that's a metal coil of wire that you can see there. To make the magnetic field a lot stronger, an iron nail or a C-core can be placed inside the coil. This is the basic arrangement of an electromagnet. This is one that's been made in real life there. You can see a coil of wire around an iron nail and it's attached to a battery. Here is a practical task you could try. Your aim would be to find out if decreasing the number of coils on an electromagnet changes the strength of the electromagnet. The apparatus you would use is a lab pack, connecting wires, crocodile clips, a C-core, a coil of wire, and paper clips. You would want to draw a diagram of your setup, describe the steps in the experiment, draw up a results table that looks like this, write a statement to show what happens to the strength when the number of coils decreases, and then evaluate your experiment by writing a statement to describe an improvement in experimental safety, and write a statement to describe an improvement in experimental procedures. Here we have a diagram of an electric bell. We can see a bell at the top, a striker, a contact, a spring, and a switch. We're going to go through and I'm going to explain how an electric bell works. First of all, an electric bell contains an electromagnet. When the switch is pressed, the circuit is complete. Because the circuit completes, there is then a current flowing. As the current flows through the circuit, the electromagnet attracts the striker. As the striker moves towards the bell, the contact is broken just here. This causes the current to stop flowing and the electromagnet is now switched off. The spring pulls the striker back and the contact is reconnected. Because the contact reconnects, the current starts flowing again and the whole process starts again and will continue as long as the switch is closed. Here we've got a diagram representing this. It's animated and you can see that we have our switch closed, and so initially the current is able to flow. And when the current flows, this part just here on the striker is attracted to the electromagnet, so you can see it hits the bell. Because it's attracted, the circuit breaks just here, and so then it turns off and the striker is not attracted to the electromagnet anymore. Because it's not attracted, the spring pulls this back here, and so the striker moves away, and our circuit is connected again, and this happens again and again and again. See if you can name all of these parts of the bell. Pause now to give yourself some time. Let's go through the answers. Number 1 is the bell. Number 2 is the striker. Number 3 is the contact. Number 4 is the switch. Number 5 is the electromagnet. And number 6 is the spring. Now we're going to talk about the magnetic relay. The magnetic relay is an electronically operated switch. Here is the diagram. When the switch S is closed, there is a small current in the electromagnet. Here is the switch there. The magnetic field produced pulls the pivoted armature towards the magnet. So there's the pivot and there's the armature. If I show you here, this armature is going to move towards our contacts here, and it's going to push them together. This causes the armature to push the contacts together, and when the contacts touch, this completes the second circuit, switching the motor on. When switch S is opened, the electromagnet loses its magnetism, and this releases the armature, allowing the contacts to open and the motor to stop. So this is where it's being attracted just here. When switch S is closed, the electromagnet turns on and the armature is attracted, which pivots, pushes this round and closes the contacts. When we open the switch again, this stops being attracted. The armature does not move towards here, so it can move away a bit, and this does not push the contacts, and so the contacts remain open, and so the motor cannot turn on. Now try naming the parts of the relay. Pause here to give yourself some time. Let's go through the answers. 1 is contacts, 2 is the electromagnet, 3 is the switch, 4 is the armature, and 5 is the pivot. When a conductor cuts across the lines of a magnetic field, a voltage will be induced across the conductor. This can be done by moving the conductor or moving the magnetic field. You can see just here we've got a magnet, and we could move this through the coil of wire. This would induce a voltage. From practical work or research, it can be shown that the size of the induced voltage will depend on the magnetic field strength, the number of coils, and the speed of the motion. It will also depend on the angle at which the field lines are cut. Induced voltages are very important for the operation of devices called transformers. Not these types of transformers, but these types of transformers. You may have seen these outside before. They're very large. You find them in lots of different places. But why are they important? Why are transformers important devices? They are essential for the transmission of voltages from power stations to our homes. There are two main types of transformer. A step-up transformer increases the voltage from a power station. This means that overhead cables carry extremely high voltages. That's 400,000 volts. We've also got step-down transformers, and these decrease the voltage. These transformers ensure a relatively small voltage, so 230 volts, is supplied to our homes. Step-up transformers. Here is a diagram of a step-up transformer. We have an input on the left-hand side, which is a primary winding, and we have an output on the right-hand side, which is the secondary winding, and this has more turns than the primary winding. Step-down transformers. Again, we have an iron core, a primary winding on the left, and a secondary winding on the right. The secondary winding this time has less turns than the primary winding, so it's the opposite from a step-up transformer. Transformers operate by having a changing magnetic field created on their primary side. This changing magnetic field induces a voltage in the windings on their secondary side. In a step-up transformer, the secondary voltage is greater than the primary voltage. The voltage has transformed up to a higher number. In a step-down transformer, the secondary voltage is less than the primary voltage, so the voltage has transformed down to a lower number. From practical work or research, it can be shown that the following equation applies to both types of transformer. NS over NP equals VS over VP, where NS is the number of secondary turns or coils, NP is the number of primary turns or coils, VS is the secondary voltage, and VP is the primary voltage. Here's an example we can try. Model power transmission lines are set up to show how electricity is distributed from a power station to consumers. A. State the purpose of transformer Y, and B. Calculate the secondary voltage from transformer X. So let's have a go at part A first. State the purpose of transformer Y. We know that transformer Y is a step-down transformer, so that decreases the voltage. And let's have a little look at part B. Calculate the secondary voltage from transformer X. So first of all, let's write down what we have and what we don't have. So we have NS, NP, VS, VP. Our secondary number of turns is, if I get my highlighter, that's just here, that's our 960. And our primary number of turns, that's the 120 just there. Our secondary voltage is what we want to work out, that's what the question is asking us just there. And our primary voltage, we can see in the diagram just there, there's 2.5 volts. Remembering back to our equation, we have NS over NP equals VS over VP. Plugging in our numbers, we've got 960 divided by 120 equals VS over 2.5. Now we want to rearrange this. We're dividing by 2.5 currently, so we just want to do the opposite. We have to times by 2.5 to take it up to the left-hand side. So VS equals 960 over 120 times by 2.5. You could either put this all into your calculator now, or you could simplify your fraction and then pop it into your calculator. Simplifying our fraction, 960 divided by 120 is 8, so we're just doing 8 times 2.5. That gives us a final answer of 16 volts. At a power station, a transformer is used to step up the voltage 20 kilovolts to 400 kilovolts before it's transmitted by overhead cables. There are 3,000 turns on the primary coil. Calculate the number of turns on the secondary coil. Let's write down what numbers we have and what we want to figure out. So again, NS, NP, VS and VP. Looking at our question, we want to work out the number of turns on the secondary coil. So that's where we put our question mark. And we have 3,000 turns on the primary coil. Our secondary voltage is 400 kilovolts and our primary voltage is 20 kilovolts. Oh, got them the wrong way around, didn't I? 20 doesn't go there. We have our secondary voltage of 400 kilovolts and our primary voltage of 20 kilovolts. Remembering kilo means times 10 to the power of 3 or times by 1,000. So 400 kilovolts is the same as saying 400,000 volts. And the same with 20 kilovolts, that's the same as saying 20,000 volts. Now we can use our equation. NS over NP equals VS over VP. So that's us putting NS over 3,000 equals 400,000 over 20,000. So rearranging this, we want to take the 3,000 up onto the right-hand side. So NS equals 400,000 over 20,000 times by 3,000. We can simplify our fraction. 400,000 divided by 20,000 is equal to 20. So our equation turns into NS equals 20 times by 3,000. So we get a final answer of NS equals 60,000 turns. Copy and complete the following table. You can pause here to give yourself some time to copy the table. Now we're going to go through each solution one by one. So here we have to work out NS, and we're given NP, VS and VP, and then we need to state whether it's a step up or a step down transformer. So using our equation, NS over NP equals VS over VP. Normally I would write down the numbers on the left hand side, but here, because we're given them in very clear format in the table, it's not completely necessary. So we have NS over 450. So we're just plugging our numbers in directly. We've got VS, that's 690, and VP is 230. Now we want to rearrange this. We need to bring the 450 up onto the right hand side. So we have NS equals 690 over 230 times by 450. Again, we can simplify our fraction if we'd like to. 690 over 230 is equal to 3. So NS equals 3 times 450. So our final answer is 1,350, and that's turns. Now we have to state whether this is a step up or a step down transformer. We can see that the number of turns on the primary coil is less than the number of turns on the secondary coil, so this is going to be a step up transformer. So it's increased the number of turns there. Here's our second question. Using our equation again, NS over NP equals VS over VP, we have 800 divided by NP equals 120 divided by 6. This time I'm going to simplify the fraction on the right straight away. 120 divided by 6 is equal to 20, so we can now write our equation as 800 divided by NP equals 20. We want NP to be by itself. We don't want it to be the denominator of a fraction, so we want to take NP up onto the right hand side by multiplying. So 800 equals 20 times by NP, but now we have a 20 next to the NP and we want the NP by itself. So we can take the 20 and divide it on the left hand side. So NP equals 800 divided by 20, and so our final answer is 40, and that's turns again. Now to find out whether it's a step up or a step down transformer, we can see the number of turns on the primary coil is less than the number of turns on the secondary coil. So again, this is going to be a step up transformer. We've increased the number of turns. Here is our third example. Again, using our equation, NS over NP equals VS over VP. We have 125 divided by 750, and that's equal to our secondary voltage divided by 24. Let's get rid of this 24 by multiplying it up on the other side. We've got our secondary voltage equals 125 divided by 750 multiplied by 24. We can simplify our fraction. 125 divided by 750 is actually going to equal a fraction again itself. That's 1/6. So we don't need to do that if we don't want to, but you can do. And this gives us a final answer of 4 volts. Now to figure out whether it's a step up or a step down transformer, we can see that the number of turns on the primary coil is greater than the number of turns on the secondary coil this time. So this is going to be a step down transformer. You've gone from a high number of turns to a low number of turns, or equally a high voltage to a low voltage. And here's our last solution. Again, NS over NP equals VS over VP. So 50 over 500 equals 23 over our primary voltage. Let's take this VP and multiply it up onto the left-hand side because we don't want it to be a denominator. So VP times by 50 over 500 equals 23. We can simplify our 50 over 500. That's equal to 0.1. Oh, we don't want an equal sign there. It's still multiplying. VP times 0.1 equals 23. And now we can take the 0.1 onto the right hand side by dividing. So our primary voltage equals 23 divided by 0.1, and that gives us a final answer of 230 volts. Now to determine whether it's a step up or a step down transformer, we can see our primary number of turns is greater than our secondary number of turns, so this is going to be a step down transformer. Again, you can see we started off with a high number of turns and we stepped it down to a low number of turns. Exactly the same with the voltage. We started off with a high voltage, we step it down to a low voltage. Here are the answers laid out in a table for you.